as an SoC, as a system on chip. So is it worth the or when is it better to use a pure FPGA, where pure microcontroller, or when to use the FPGA or SoC, including the FPGA? So this is usually the hardest question, the toughest one. The toughest because the programmable logic, in fact, needs a lot of effort to be programmed. We were talking about it a bit during ITMs. Mr. Vujicic tried to convince you to use it a bit, I think, then during laboratory, so at least to try to make some basic programming about the FPGA. Yeah, today I would like, just because we don't have much time, but I would like just to remind you about the main methods of programming the FPGA in practice, the main methods, and why this is so unpleasant. In fact, this is so unpleasant from practical point of view. In general, what's good about the FPGA, it's something, and about the SoCs with the FPGA, what is the major positive feature, the major element why we like the FPGA is the scalability. So first thing is the scalability. So this is the first feature that we can get from both the FPGA and the SoCs, including the FPGA. So it's very easy to increase the size of the algorithm to make it more complex, and then this is usually eating up some resources, but it's not influencing the execution time or the performance of the whole system. That's not the case in microcontrollers, as you know very well. So if we increase the complexity of our program, if we scale up the algorithms, then we have to pay for it with the performance. So this is the first feature why we like, or whether FPGA as a heart of embedded system is favorable. Second thing is parallelism, something like this. Because in case of FPGAs, any kind, we can really make a trade-off between the resources that we sacrifice for such an operation and the number of and the speed, and we can optimize it. So we are not stuck, like in case of microcontrollers, to the resources already existing, and okay, we can manipulate sometimes with the resources, and we can try to sometimes we have a chance, but only sometimes in some microcontrollers, especially in multiple core microcontrollers, to offload some tasks and put them to other units if they exist, but that's not very popular, and very often in microcontrollers we are talking about asymmetric units, which means that not really the offloading of heavy calculations is not really possible in the case of those structures. In case of the FPGA or FPGA based SoCs, that's pretty easy to do something new, to add some complexity, to add some block that will speed up our calculations. So we will eat some resources, but we will speed up the calculation. So yeah, graphically, we have the situations like shown here, so that if we need anything, if there is anything missing in the main hardware processing system, we are just adding some peripheral block here, and it's done. So this is definitely an advantage of this kind of solution. Not mentioning the bare FPGA, where we can do anything we want, anything we need. And then So this is the second decisive feature, and the third decisive feature, so the deal maker, so in case of FPGA based chips, is the size. Is the size comparing to the microcontrollers. That's sometimes a disadvantage, but here I mean the size in physical size, not scalability as the algorithms, but the physical size, where we need, for example, to drive, I don't know, 100 LEDs, any kind, or 200, or we need to read 20 sensors. Because in microcontrollers today, you can find microcontrollers with as many as, for example, 6 SPIs, 4 UARTs in one package, which is pretty nice, and which is good enough for very many applications. Yeah, but then sometimes it happens that, okay, you have 6 SPIs, but you need 7 or 8 or 20. And then, even if this is just the case, even it's just if it is just about integrating so many resources, simpler resources, even if the resources are not, they don't need to be very high, very fast, then still this is the case for at least for small CPLDs, but usually for small FPGAs, to cope with this problem. Or if we want to make a single chip solution, then we're using SoCs with either the FPGA and CPU, or this kind of SoC that you've got on the slide with the CPU, FPGA, and some vector processor to have the very high performance, especially in graphical and neural network applications. And we can also add here a fourth feature, extra feature, fast networking. That's also pretty standard and pretty discerning feature today between the FPGA and the microcontrollers. That's about, we mentioned about it last time a bit, so that we can expect from microcontrollers, from a programmable logic today, we can expect fast transceivers, so the blocks that are translating the parallel into serial and serial into parallel, and not translating at megabits per second in megabits per second range, but into gigabits per second range. To be honest, from practical point of view, it's really difficult problem if we would like to do it without FPGA. It's such a situation in the market that, okay, because you could try to, for example, you could think about having a microcontroller with a separate interface chip translating parallel output of a microcontroller to a single differential lane, single bit differential lane at gigabit speed, but there is nothing like this on the market. You can find an ASIC chip or ASSP chips doing this, but this are difficult to find and pretty expensive. Which means that this is the realm of the FPGAs or FPGA-based SoCs, definitely a real. So if you think about going into gigabits per second per lane of transmitting this kind of data, then this is it's a synonym, I would say. So fast networking, FPGA. So this is then a clear thing to choose. Of course, the difficulties are resulting mainly in case of FPGA from the very tight connection with hardware. And this is really the most difficult part. So it's not only about the language, because the programming language, yeah, we'll try to remind it a bit in a moment, but the language itself, okay, it's a bit rusty, it's a bit outdated comparing to new languages existing on the market. You can try, so there are various trials even to implement a Python or a C, more successful with C, less successful with Python, but who knows what's going to happen in the next future. So maybe even you'll be able to use a Python. Okay, you can use graphical as well connections, and you can try to use the IP cores, which is the case in Vitis and Vivado today, for example, as programming environments, so that we are trying to build everything or as much as possible from blocks. But even if you build everything from blocks, even if you try to use a Python, if there is a Python or this kind of language for designing your application on programmable logic, it's still not enough. It's still not the solution of this problem, because the major disadvantage, really, the major minus thing is the is linked to hardware. So, or link of what? A link of software and hardware, which means that you can try to escape. You can try to escape the logic below, but you are not able to. It's one of the reasons we put so much effort and we lost so much time on trying to teach you how to work with logic during ITM course. Because in order to be a good designer of applications on FPGA or FPGA based SoCs, you must know how the logic works. There is really no shortcut, because there is really such a problem. And that's also the reason as well that there are many people failing to make applications on FPGAs, properly working applications, or people escaping these nice features that we are having here because they are afraid of FPGAs. Because really the link to hardware is here clear. So if the hardware engineer today has to know the electronics, but has to know as well that the FPGA, and that there is some logic underneath, and there is some propagation, and there are some problems with the possible problems that need to be overcome with clocking, with clock jitter, and with clock skew, and with those setup and hold times. So you must be able, as this kind of hardware engineers or specialists in hardware programming, has to be able to discern this problem and solve this one. So programming at the level of course, at the level of system C, theoretically, so it is possible, but you are not able on FPGA to stay only at this level. So at some point of your project, you will need, unfortunately, to get down to hardware, and this is really the most difficult part from practical point of view, because and then going back to our hardware description language, this is really not that difficult. Okay, it's different. As a reminder, because we have already done this some time ago. So the process is a bit different, because we have this. We are designing a hardware. So we are designing actually. Let me show you. Yeah, this slide I wanted. So we are designing in practice connection of elements inside. So that's a different paradigm. So we have to think differently about it. So that's why we're using different language. But all in all, to be honest, that's not such a problem. So the main issue, from my perspective, is actually this link to hardware. So that it's always about the necessity to have the hardware at the back of your head, so that there is still something underneath. So even if you are designing, even if you are trying to use on the system level, trying to work with some high-level constructs, which is possible in description languages today, still to have it optimal, still to have it running, you need to think how it will be. You need to have at least a vague idea how it will be implemented physically. So what elements will be incurred from your logic, from your description, and how, maybe not to the gates, but what kind of elements will be the results, shall be the results, or are the expected results of your design. That's the issue. That's the issue. And then returning back, so making a fast sweep through the most important elements of the language itself. So the language, just two languages on the market. So it's really about deciding which one you want to choose. It's about Verilog or VHDL. So those two languages are giving us a chance to describe the hardware connections, both in CPLDs, in FPGA. FPGAs and then in the FPGAs inside SoCs. In case of Verilog, it's more C-like language, but C-like doesn't mean it's C because it's not. In case of Verilog, it's more verbose language that is as well a bit higher. So has higher constructs, higher level constructs. So it's easier in case of VHDL, for example, to share your code between the designs. In Verilog, the sharing it's a bit more complex. As the language is closer to the hardware, so closer to the logic, closer to gate, the connections itself. Verilog is a bit higher in the hierarchy. It's more abstract, I would put it this way. In case of VHDL, the program structure, so it's basically pretty simple. You should remember it. So we need an entity always. The entity is the declaration of the element that we are designing something with some inputs and some outputs. Those inputs and outputs are ports. Yet the entity may miss the ports, but only if it is used for simulation. Because very important element of the development of FPGA, because of the hardware issues, exactly, because of this link between hardware and software. So the very important element is the verification. So that's why we are using the same language as different subsets of the language for preparing a test bench, for preparing the code that will test another code, another entity. So in fact, the entity that we are preparing for design, for being physically implemented in some physical chip has to have ports, while the entity that is used for testing, which is above this, doesn't need ports, because this entity for testing, such an entity, then it is possible to observe, for example, those ports and to display signals, to see the signals and connect. First we connect signals, declare some signals in this entity. So here in the declarative part, we define the signals there, and then we connect the signals to ports, and observe that we are able to observe the signals. So we don't need physical connections, but only then the entity is possible. So if it is used for testing, then it doesn't need ports. If we want the entity to be translated into physical hardware, we must have ports. Then inside the entity, we've got beside the port declarations, we've got declared. We are declaring here. So in the declarative part, we are declaring some global signals. As you should remember, in VHDL, we've got signals and variables. So the containers that we are using for temporary data. The difference between variables and signals is pretty important and pretty substantial. The variables are just just values. So they are purely virtual. The variable. So they are auxiliary elements. It may be, the variable may be placed in the memory, but doesn't have to. Mark the difference between the microcontroller variables and the variables here. Microcontroller variable is always a piece of a memory. It may be a stack, it may be a place on stack, but it's always a memory, somewhere in the memory, always. Maybe optimized out, okay, but it's always, but usually it's not really optimized out. Usually it's somewhere in the memory. In case of variables in VHDL, the variables are usually just a virtual element used for describing something, but it's not a memory. It's not placed in the memory at any time. So variables are never an element in the memory because they are just virtual. So they're used for us. they have the meaning for us as the designers, but then they are just registers, connectors, gates, they're translated. So it really depends on the particular application and particular variable application. Different thing is about signals, because signals usually, like variables, in majority of cases are just purely virtual thing. Thus, signals are different. Signals are physical, like variables in microcontrollers. The signals here are physical, and signals are at least a wire. So signals are at least a connection between the element, but quite often signals are kind of registers. So with signals is physical, variable, virtual, signal, physical, and signal usually it's not optimized out. So usually it's after optimization it stays, it's renamed, but usually the signal is still with us. Why variable now? We can declare here signals and variables because they have different a bit different applications. In case of VHDL, signals and variables, they can be globally defined in entity. They can be also partly globally defined in the architecture, but they can be as well locally defined. Variables only can be locally defined in processes, and that's the major. So there are a couple of differences between signals and variables. The signals we are defining as globals, usually visible in the whole scope of our code. While with variables, we are, it's advisable, I'd put it this way, it's advisable not to declare variables in global scope. So we can use, we can do it. To be honest, we can do it. We can declare variables here as well, together with signals. Then they will have some difference about the usage, about the assignment to this. So there are slight differences between signals and variables that we will not mention at this moment. But generally, we can declare them and treat variables as globals, but it shouldn't be done. So it should be avoided. And in many on many documents about VHDL, it's highly people are highly discouraged about using global variables. So global should be just signals, while variables should be kept local to processes, to procedures, and to functions, because in procedures and functions we are declaring only variables, so we are not able to declare signals there. Only variables, so variables should be kept local to processes, functions, and procedures. Signals can be made global in declarations in the entity. Signals also can be made global and put in packages, because in packages we can also add signals, although that's not a good idea, that's not a good practice as well. So signals should be kept, again, global, but within an entity or within the architecture. Internally, the structure of the program, again, something you should remember, begins with the libraries, and then we've got our entity with mainly ports and some declarations, and then we've got the architecture with the declaration part first, and then the so-called concurrent part. In the concurrent part, we've got the expressions, a couple of expressions. We'll sweep to them maybe after a short break. Inside one of the expressions in FPGA in the VHDL itself is a process or procedure. Process or procedure is a place where with sequential execution, I would say, because of course here nothing is executed, but it's translated into some hardware, but at some level of abstraction, we can say that these expressions are executed. So we have here at this example 3 expressions, 1, 2, 3, where the whole process is just one expression. those three expressions are, let's say, executed in parallel. Of course, they are not executed, but from those expressions, there is incurred a separate piece of hardware. That's why we can think about having them executed in parallel, but in fact, there is a different, separate piece of hardware, incurred from those expressions. In case of the process is the place where the execution is sequential. So when there is a sequence, sequence matters. So if you assign to some variable, here it matters the sequence of assignment. So if you assign to a variable 1 and then assign to a variable 2, inside the process it matters. If you assign to a signal here in this part twice, it not only that it does not matter, but also it will cause an error usually, and the compilation, the synthesis will stop, because this caused such an assignment causes this ambiguity about which value should be really assigned to X. That's not a problem here, because here we've got, first we assign 1, then we assign 2, then we can assign whatever we want. In case of the assignment to signals in the concurrent part, it's forbidden, because concurrent means that if we assign in 2 lines different values, then it is understood as if we assign at the same time to values, as if we would like to assign to values at the same time, which is of course not possible. Possible physically, but physically it means connecting two gates to one input. Which gate wins? Who knows? That's why that's not possible. That's not that's one as well, one of the difference between a signal and a variable. That with signals we can't assign, we have to be careful with assignments. With variables, not really, so we are just assigning, and it's done. The question, so in case of the program structure, a very important element is how the program structure, because this is the program structure of a simple code, but the very important element is how the program looks like, the large program, how does it look like, because this is small code. So if we have a few thousand lines, maybe, then it looks like this, so that we have these 3 parts of library, entity, and an architecture. But what if we want a larger program to build? Then we need to be able to split, to take a part of our code, for example this one, and put it somewhere. In C we are using functions, in C++ we are using methods. Here we can use procedures to do this, so there is such a chance of using a procedure, yet logically it's much cleaner and better to use, of course, a component, which means that we are building a code like, normally we are building a program structure like this one, like shown here at this slide, where we have a part of the code cut out, so a code divided into parts, but the parts are then separate components. So we are not using for this purpose procedures, although we can, or functions, although we can. Rather, we are using components for this purpose. This is much more VHDL style. So functions and procedures can be used, but it's much more about. It will cause some problems when using FPGA programming. Structurizing the code should be done, and is usually done by splitting the code into components, and then instantiating components, combining them together to form the final entity. Component is actually an entity, and a component can be composed of other components, which means that an entity can be composed of as many entities as we want, and there is no limit in the level of nesting. Now maybe you can try to make a nesting level of 100 or 200, maybe you'll run out of memory, but that's the only limitation during the synthesis process. but that's the only limitation. Normally we can have any levels of nesting of the component, but that's the way we are. That's the structure we have usually in the HDL program, combining the components together and forming the final entity. Okay, in case of from the important things, yeah, here it is. So that's how it usually looks like. So the structure. So we have the entity with declarations if necessary, the architecture with declaration, of course, one entity, one architecture, and then in the entity we've got the component. Because component is exactly an entity, it means that it does have ports. It does have ports, although it does have ports, and that's the method we are instantiating the component. We are connecting ports between the component and the ports of the entity, or the signals, because we have here in this example they are just connected ports together, but let's consider we've got additional port and we've got some signal defined here. So we can connect a port of the component and a signal, because port of the component is exactly has the same properties, and if this is the same data, if this is the same data tape, then you can connect signals and ports together. So this is the structure of the element. In case of the ports and data tapes, the difficulties or the strange thing about VHDL is there are different naming of the data tapes, because in fact most of the data tapes are existing everywhere. So like composite structures, like the pointers, like simple scalar enumerated integer or real data tape. What's a bit extra is the data tape of file, data tape of physical, which means that we can have signals of tape time or of tape file, which is used, of course, the file is used for transferring the verification information to and from our design. That's why we are using file. The major data tape used in VHDL is enumerated data tape. The second most common use is integer. We have the data tapes like character, like string, and we are using them as well from time to time, but they are much less important compared to C. Same is with access, so with pointer, because access data tape is a pointer. Again, it's something that we are not really using in VHDL. So the whole code in VHDL, in fact, you can build based just on one data tape, on STD logic and STD logic vector. So the master is because vector is a combination of STD logic bits. So just one data tape. So you don't need to use more in FPGA. It's, to be honest, we are sometimes mixing integer and STD logic or STD logic vector because integers are better for arithmetic operations. The other data types are pretty rarely used in VHDL. In case of design, for verification, yes. So if we are building the verification platform, verification test bench, then we are using everything. But for normal construction, it's so simple. Then one data type or maybe two data types, so STD logic vector and integer, and they are covering usually all our needs in case of VHDL. Important thing to know maybe as well from practical point of view is that we've got strict tape control. It's classic in VHDL. So we have, it's case insensitive. That's kind of a, so no limitation from this side. So we don't need to think about keeping the letters high or low, although it's just a feature, it's not positive or negative. In case of strict tape control, it's again a feature. We can't say that it's negative or positive because it's just a feature. So that C is in C we can assign character to pointer or pointer to float. Whatever we can do whatever we want. Here now, here we have situations where left side of the assignment and right side of the assignment have to be exactly the same data types. So integer and integer, std logic vector and std logic vector. But even in case of vectors, if on left side we have the std logic vector size 4, size 5, size 6, then the right side of the assignment has to be as well std logic vector size 4, 5, 6 respectively, so that the tapes must match. Both data types must match completely. Okay, let's have a short break. Let's have a break, and then we meet at 12:15 again. Okay, welcome back. After a short break, let's go further. So in case of the data types, so they are basic data types. You've got them in the documentation. So nothing. So they are, of course, but as I mentioned, the basic ones are just the std logic vector plus the integer. Sometimes you're using some modifications, some extra types like signed, unsigned, or bit vector, but these are the only ones. So that's for the case of the program. It's usually the only. It's so simple. It's usually so simple. There are not so many choices. Yeah, in case of the language elements, small reminder or a small review. Constants, standard thing with standard methods of defining a constant common to the VHDL. So we've got the element of the VHDL syntax, so the name, so constant, variable, signal, whatever is there, then we have a name. As the second element, a colon, the data type, so integer, std logic vector, maybe signed, unsigned, and for some reasons. Then we've got the assignment, two methods of assignments here. So we've got either colon and question mark. Second assignment is with the is this kind of assignment with greater mark. The difference scope of usage. So this kind of assignment is usually for signals. This kind of assignment is for constants and variables and for initial values. So mainly it's like this. The equation mark is just a logical operator. So it's for testing if something is equal. So it's the assignment is always with two mark element. And then we have a value in case of the constant. So that it's that simple. It's that's trivial. Then about literals. Literals in VHDL, it's yeah, they have to be viewed with special attention a bit. It's not very difficult, but they have to be viewed in special attention. So the literal with decimal point are of type real. The literal without the decimal or with the exponential form, engineering form or exponential form, whatever the name, they are both real type, while the literal with constant is just an integer. When we put a number, if we want to have a bit, then we have to make a literal with a notation of hexadecimal or a binary notation. We can have the, because this is decimal notation. This is decimal notation, so we need nothing extra here. But if we want to assign integer in hexadecimal, integer in hexadecimal, we need to use hashtags with the base. So the base here is 16 or 2, but we can have any base. We can try to use any base between 2 and 16 here. So of course you can even have 10 hashtag 127 and hashtag again. It's gonna work. It's possible to use the underscores, any number of underscores, just to make everything clear, so that you can easily read longer numbers, especially. So these are white signs, so these are not included into the analysis here. There may be literals as well of time, so numbers, but we have the data types of time, so there may be literals of time. And of course, there are literals of enumerated types. So 4 type of literals. These literals, that's not a problem if we talk about the literals for single elements, single enumerated elements. So For example, we are defining with tape a new data tape of MyLogic, which is the enumerated tape having 4 elements x 0, 1, and z. And then we assign to this tape, to the signal constant variable, whatever, of this tape, using exactly this literal. So if there is an apostrophe 0, then we are using apostrophe 0 apostrophe. If we have an idle as a symbol, then we are assigning an idle or read or nsig, psych, whatever. So that's so simple, but that's simple for the case of the literals which are single literal. What about the vectors? Then with the vectors, everything gets a bit more complex because the vector is a combination of enumerated elements. So in our case, for the bit, so this is my logic tape, but the tape bit, because we have bit vector here in this example, tape bit consists of just 2 elements in the enumerated. In the list of values, it's 0 and 1 in apostrophes, and we combine them to form a vector in double quotes, not in apostrophes. So it's not a combination of 1, 1, and so on. Of course, that's not this. We are using it in apostrophes. In double quotes. The same is with an array, because vector is actually an array, because this is the name. Bit vector is an array. Formally, it's an array of values. It's an array of bits. In case of string, this is the name of array of characters. Character is one character, one letter. It's one character from ASCII table. So a string is an array of characters, and as such, as well, we put it in double quotes. But what if we would like our literals in case of bit vectors or std logic vectors, which are very often used? What if we want those literals to be written not in a bit form, but if we want to combine them together a bit to shorten the numbers to form some hexadecimal or octal numbers? It's different than the literal hexadecimal literal used for integer. Take a look, because in integer we are just placing that we want a base of 16, and then we put a pound hashtag, and then we use the hexadecimal values. In case of, but this is integer, it's a number. Here, this is something extra because normally, formally, a vector, a std logic vector, a bit vector is just an array. So we should write to an array, right? Like we are doing in C, that we are filling cell after cell. In case of the bus, in case of the literals in std logic vector or bit vector, because these are usually used, but also signed, unsigned, so there are various data types, being the array of enumerated bits, or being so in this case we are using, there is a special tape of literal with letter B, O, or X. Different literal, minded. Different literal. So if you have an integer, let's say I, then it's not possible that you assign A, B, C, for example. That's not good. It will be a tape mismatch, because this literal, this one, is of std logic vector or bit vector compatible literal, not integer. That's also a feature of VHDL, that it's two different literals in case of hexadecimal, and you have to know which one you are using and what you are assigning. So it's not that simple. It's not that obvious when you're writing a code, especially when this is your beginnings. In case of operators are slightly different. The problem with operators in VHDL is that it's very tricky game sometimes, which one is for verification and which one you can use for development or design. So of course, all the operations are can be used in for the verification. So for writing, preparing kind of a test bench. But whatever you want, whatever you need for the operators, for the design is pretty limited, and sometimes it's sometimes some of the operators like multiplications or divisions are not very optimally implemented. If we use just in code, that's also a bit nasty about the FPGA. That yeah, we would like to. We can add two symbols, so we can write C is A plus B. It's gonna work. This plus operator works. But if you want to use A multiply B, it's questionable. And if you want to use C is absolute of B of A, usually it's not gonna work. It's not gonna synthesize because it will work in verification state. So if you would like just to simulate something, but if you want to make it running, if you want to synthesize it, not really. But there are some nice operators like modular, like reminder. Very important operator from practical point of view is a concatenation. So combining two things together. We are using it to concatenate usually enumerated data type. So then we have two smaller vectors and we are building one larger. So in VHDL, it can be done very simply with just ampersand operator. That's not possible in the classic one. Yeah, in C, we don't need to. We can do it, of course, by assigning a part, copying this vector to a larger vector, and forming one large vector. But the concatenation here simply works. Various operators, logical, and so for shifting left right, for rotating left right, from logical point of view, they are not so important, as we can do it pretty easily with assignment. Nevertheless, they are there. Standard relation operators, so testing for equality, inequality, being larger, smaller, and then various logic operators that you know very well from C. This time here in VHDL we are not using the symbols, just we are writing the operators, and we have some extra operators like NAND, which is not available in C. All the operators can be overloaded. This is very important functionality, something you know from C++, especially in C, not really, but the operators overloading plays a very important role because of strict tape control. And it means that for example, if you want to make your new data tape enumerated or based on some existing data tapes, then usually making a new data tape means that you have to prepare the operators for this. So that's something you do in C as well, because consider making a new class and you want to add two objects of two classes together. Yeah, there is an operator of plus missing, so you have to make this operator. Well, same situation here, just that you have to do it even at very simple level, even with very simple data tapes, because really this is missing, and the strict tape control here is sometimes difficult, to work with sometimes. Yeah, signals and variables, we did make the difference already. So variables is basically local, and it should be kept local, so we can define it globally at a global scope. But the problem in case of VHDL from practical point of view, is that we have too many globals. We have too many globals. Today, we try to make variables local, and we are even doing it local in such a way that they are just defined in very tiny scope of one loop, and so that they don't build this declaration part, they don't build it too much. In case of VHDL, it's difficult to be done. So we can make, because unfortunately the signals are global, and it's very easy to end up in a situations where the declarative part of the entity or the architecture, because usually the signals are declared in the declarative part of the architecture, where this part has 20, 30, 50, 100 lines, because so many signals are there. So we should avoid, we should push as many variables, declare as many variables as possible locally. So to keep them inside the process, to keep them inside the function and procedure, not to reveal them at the top level, not to obscure all this declarative part, because it's unmanageable really, if you have 50 signals. And yeah, you start adding new ones because you get lost with what's already on board, with what's already in use. So that's why variables should be kept local. Plus the variables have some extra features that they are, whatever you write to signal in process is updated only at the end of the process, while whatever you write to variable is updated line by line. So any write is valid. Yeah, the process is part of very important, very vital part of each VHDL code. The process itself is a concurrent statement, but it's a sequence of sequential statements, and the statements in the process are done sequentially. It's a very important part of the VHDL program, and usually the major complexity is in the processes. So usually the program is based on a few concurrent expressions, and out of the few concurrent expressions, usually most usually the processes eat out majority of the space. That's from practical point of view. All the processes are run in parallel, and all the processes start in parallel. But again, thinking hardware, that's what I was starting with today, because the process is a piece of hardware, separate. So each process, one piece of hardware. So a process can be a counter, a process can be an arithmetic logic unit, a process can be a microprocessor. So each process, one piece of hardware. That's why run in parallel, normal, because it's different hardware, it's different topologically part of FPGA usually. Process communicates, process formally at the higher level of abstraction can be suspended. In the process, we are doing quite complex control applications. And again, from practical point of view, the process very often, if our process, because we are usually writing our code and usually we are putting more and more things in the process is usually sequential to some clocking. It doesn't have to be, because the process may be a source of combinational logic, but quite often the process is synchronous to some clock, and what is happening in a process is sequential to some clocking. That's the most common use of a process. Because it's sequential to some clocking as well, we can stop it, we can pause it for some time in simulation, and that's very convenient. Waiting for some event or waiting for some clock in the design part. That's how we use the processes in the design part. The process communicates with the rest of the design with signal and ports defined outside the process, and that's the reason of problem. That's why we need so many external signals. In fact, because this is not a function. The process has sensitivity list, Yeah, here is how the process looks like. So we've got the sensitivity list of the process, but it's not the input list. So it's not that these are the input arguments, because this is not a function. That's different. So although the notation seems simple, but that's not a function. We don't have an input here. So this ABC are just the signals that the process is sensitive to. And there is no return as such. So we are here in this example, there is assignment to X, but the X has to be defined outside. So this is usually a signal, but maybe a variable as well, global variable, but again, we avoid it, but usually it's a signal or a port. And this is the explanation why we need so many signals and so many ports being declared as globals in the architecture or entity, and why this is so nasty, why this is so problematic, because we can't really call process from a process. The processes cannot be nested. That's also important. Inside the process, there must not be another process. This is just this is pretty flat structure in case of processes. There can be, the processes can share some signals. So one process can modify a signal that another process will read. But for example, two processes must not modify one signal or one variable. So if there is a global variable, it can be modified just in one process, can be read in another process or processes, but we must not modify port, signal, or global variable from different processes. That's the rule. Again, resulting from hardware. So once again, hardware at the back of your head. So why can't be defined, can't be changed? Because one process would like, let's consider a signal C or can be signal Y. And one process would like to set 1 to this line, another process would like to set 0 to this line. What should be the value of Y? We don't know. Synthesizer doesn't know. It doesn't allow this. It's so simple. Okay. There may be a weight in the process. So going into details. So we may omit the sensitivity list, and then we need to wait. We need to add an event that the process is waiting for. So it's either this or this, but for that's about the synthesizable part, so the develop design language. If you want to make a verification, then if you need to build some verification program, then it's easier. Then we can use inside the process any number of weights, and we can even use such a nice weight, so waiting forever, which is maybe not so important or so nice, but what is nicer is we can wait for some time. That's possible only in simulations, in verification. It's not working in design. In design, you get an error if you start to use time. Again, hardware at the back of your head. Why? Who is going to count the clock? Who is going to count time? There is no universal time source inside the FPGA, so we can't use this universal absolute timing in practice, in design and development, just for verification. But for verification, it's possible. So why not to use it? We're using it very often. To be honest, we're using this kind of wait for some time or wait until something happens. So we're using it very, very often in simulation. In verification, not really. In simulation. That's true. Important thing from practical point of view, so here in capital letters, that the signal assignment are made at the end of the process evaluation. It works this way that it's an advanced feature, but it's maybe worth to know that, yeah, you can try, for example, to assign to signal 0, then 1, then A and B. In fact, all those will be yeah, it's not going to cause an error. It's not going to even cause a warning usually. It will just be neglected because only the last assignment will be taken and will be valid. So forget about LED blinking. this way, like you have it in the microcontroller. Then we assign to a port some value, then after then some value, then some value. No, it's not going to work this way. If you want to make this kind of LED blinking or port control, you have to make state machine. You have to make a state machine synchronized to a known clock source. This is the only way you can do it. So it's not so simple as you can see. It's not so simple as in microcontrollers. Again, why? Hardware at the back of your head. We've got in microcontrollers, everything is synchronized to a clock. So every instruction is synchronized to a clock and follows the clock. That's why you can assign a value, and then after some time you can assign a value, a different value, because they are synchronized to a clock. Then it's happening in some time shift. Here we don't have a time shift because we are assigning, and then we are assigning, and then we are assigning. It's happening at the same time, physically. So only the last one is taken. It's not causing an error, it's not causing a bug, but it's only the last one is taken in case of the process. Sorry, that was one important thing. Tips and tricks. So if we are discussing about this, first tips and trick, there is no physical elements in VHDL. We have operators. So we can write C equals A and B. So it seems it's gonna be a gate. It's gonna fulfill the logic functionality. So C will be A and B, and there will be the output of C will be, of course, dependent on the state of A and B ANDed together, but we have absolutely no warranty and AND gate will be used. Same is with flip-flops, same with other logic structures, even the basic ones. So VHDL is higher than this. We can have it in, we can try to play with it in Verilog, because Verilog is a bit lower, but in case of VHDL, we don't have physical access to the logic structures, at least from Verilog. From VHDL, we have the access with various other methods like attributes, like dedicated extra software in the environment. We don't have time to talk about it now, but from the VHDL point of view, from the VHDL level, this level has much higher level of abstraction. So we have no direct elements, logic elements included. And next even more important thing, because this is okay, it's just a feature, not very important. But the next important thing is that required logic is inferred from VHDL description. Doesn't sound scary, doesn't sound important, but believe me or not, but a small change in the structure of the code causes a lot of differences in the final logic. You can think about it as about the Karnaugh mapping and about fulfilling this missing this x's, this field with x, not with zeros, for example, which were expected, but filling them with ones, and then having, instead of a gate with two inputs as the final solution, having a combination of multiple input gates and of nots, ands, and ors. You can think about it this way. So functionally the same, but the structure completely different. And that's exactly the thing that's happening in VHDL, just on the larger scale, is that we need to cooperate. Whatever we write, we need to cooperate with a synthesizer to get the final effect. What means cooperation? It means that we need to use, so, okay, you can do anything as long as you are using the structures which are recommended to you to be used in VHDL. There are not so many structures, but there is a limited number of structures, and unfortunately, we need to follow those structures. It's especially problematic when you come from the world of C and you try to jump onto the bandwagon of VHDL programming. Then first you really get lost because you are using C-style coding with functions, not with components, but that's not such a problem. But then you try to write on the level, on the high level of abstraction, you try to write your code. and then you end up with completely unoptimal structures, eating up all the resources and not giving the requested performance. It's tiny problem. Of course, when you get used to VHDL, it seems simple. So yeah, it seems obvious and simple, but the beginnings are not that trivial, unfortunately. Yeah, this is worth to know. I'd say this is worth to know. Then, in case of VHDL, in case of the language itself, we've got the two subsets of the language structures. So the language is not very difficult. So you are trying to use it during ITM. So from the perspective of the language itself, the language is pretty simple. The language itself, which may be misleading a bit, because the simplicity of the language doesn't mean that programming is unfortunately simple. But anyway, the language itself, the elements, there are just a few elements that you must know. A few building blocks. The building blocks are sorted into two categories, into concurrent statements and sequential statements. Concurrent statements are the statements which can be used inside here, so in the concurrent area, so between begin and end keywords of the architecture. There is, of course, no order between the concurrent statements, so any sequence is possible here. In case of the concurrent statements, there are just really a few of them that are important. So the process statement is extremely important. The component, I would even say this way, the component instantiation statement is very important, because this is the statement that we are using to build our blocks, to combine the blocks together to form one code, one element. And then we've got the very important signal assignment statement. Three types, so simple, conditional, and selected. So I will show in a moment the major differences between those two. And then important is the generate statement. For code multiplication, there is such an interesting thing as the possibility to multiply a code, to multiply a hardware. The thing that's that is a bit strange at first sight, but again, if you take this back perspective of a hardware, it has a lot of sense. So consider that you are constructing a new graphic card and you want to have a matrix of processors, and instead of building the matrix laboriously, connecting everything together, you're just writing a simple if and for generate, if generate and for generate, and use this kind of structures. And then you simply, with a few lines of code, you're able to build very, very complex and very, very sophisticated structure of elements. And then as well, let's say that important is a concurrent procedure call, because we have procedures as well here, so we can use it. The other statements, like the assertion block statement, you can forget it. You can forget them. So as you can see, not too many. So the process. In case of we've already spoken about it. Signal assignment, yeah, the very basic signals you have here. So nothing really special. Although for simulation, what is a bit extra, so if you want a verification, there is after clause possible, so you can assign after some time, so which means that you can make a time shifted signal. Only for verification, that's not possible in case of the simulation. Then we've got interesting thing, we've got conditional signal assignment, which means that the assignment occurs under a certain condition. It's like if, here it's when else, which is the conditions. So we are assigning to the A in this example when there is a condition met of S0 being 1. You assign B when there is S1 being 1, and so on and so on. And if there is a kind of a switch case, which is called here with select. This is selected signal assignment, so-called selected signal assignment. So take a look how it works with select. So with variable select, like switch case. And then we assign some value when some condition is met, another thing when condition is met, and another. So this kind of things can be done. So this is important. Signal assignment statement. Block, we can omit. This is completely not important. Procedural call, very simple thing, because we are this is procedure, and such a procedure we just call. This time we've got the parameters, input output parameters, because procedure here can have parameters not only of input but also of output type. We just call it. That's it. It's so simple. And component instantiation, so very important, very important part of the language. Yeah, so we have an entity, another entity with an architecture, and then instantiations is that simple. So the simplest version of instantiation of a component is like this. We need a label, then we point which element we want to instantiate in our design. Then there is a keyword, port map, two keywords in fact, port map, and then the elements that we are, the signal ports that we are connecting together. Remind ourselves about the final structure of the VHDL code when there are the components and they have the ports connected to some signals or to other ports, or to in the entity or in other elements. That's exactly this. So it's so simple version of component instantiation. So we can have more complex versions, but we don't have time to talk about them. Now. Generate statement, it's that simple, so that we're having a kind of a loop. Mind that loop. And normally there is no loop in concurrent statement, because the loop, the VHDL hates loops, to be honest. And the loops are basically just a simplification of a code. The loops are by definition in VHDL, they're unwounded to form to multiply the code inside. So the VHDL is never using, in VHDL we're never using loops for design, for verification only. Here this loop is as well used to multiply this code, because it generate means the multiplication of this code. So instead of having the code written 40 times, we can use one loop and multiply the code 40 times within a few lines. That's how it is. Additionally, we've got the if condition, which we can use together with the for, and then we can generate, if anything is true, then we can generate some pieces of code, generating pretty complex structure. And the second part of the language is the sequential part. So the sequential statements which can be placed inside a process or inside a function. They are as well just a few statements. So we've got the wait statement, we've already talked about it. We've got the assignment to signal, the assignment to variable. We haven't spoken thus far about the if statement, about the case statement, about the loop statement as well, but this is not green, which means that it's not so important. If and case is very important. Assertion report statements are not really important because they are just for debugging. Yeah, null statement is completely not important. We've got procedure, call, and return statement. Return is for functions. Function and procedure calls are just calling of the function and procedures. Again, take a look how few components we have. So basically here, from the important stuff, we've got the wait, we've got the assignments, we've got the variable, we've got the ifs, we've got the cases. We've got the cases as well. They are very important. Loop is so important. The other ones, okay, the procedure and function calls are important. Okay, these are because we are using them from time to time. But just a few components, just a few elements, and that's it. That's the VHDL. Nothing really, nothing more. So in case of wait, we can wait for, we can wait until, we can wait forever without anything. We can wait on some signal. On some event of some signal. In case of signal assignment, it's same like concurrent. So formally it's something different, but yeah, it's even simpler because it's the same. So there is no difference between concurrent and sequential signal assignment. as well, in case of variable, because variables we can assign, if we have local variables, we assign them in a sequential part. But if we have variables defined in the architecture as global variables, as shared variables, then we have the same assignment, just the assignment is global. It's variable. Then the if statement is a bit different from the point of view of syntax, because we've got we don't need to use parentheses, so round brackets, the conditions between if and then, but we need to use a keyword then. We don't need to use begin end, because we are using the begin end here in this language, but in else we don't need to. So we may have statement of sequence between then and if keywords. If there is some else necessary, then we have else if written together. So small change, but yeah, that's the characteristic of the language. So if, else, and if it's done this way. Simple looping. So take a look. That's how the loop. That's how the decision making looks like in VHDL. In case of the case. Again, the syntax is completely different from with select. So with select at the concurrent part here, case here reminds much more about switch case. Of C, just we have no switch, just case when. So in C we've got switch case. Here we've got case when, case one. There are a few more differences here, but yeah, we don't have time at this moment to do this, to consider it so in such a way. So case temp is, and then we analyze it step by step. So similarly, you can then revert back to with select to see how similar and at the same time how different it is. Why is it so much difference? Why is the difference between sequential and concurrent case? Kill me, I don't know. Yet there is. In case of loop, just to finish the subject and the lecture itself, the loop here we've got theoretically 3 loop types. So simple loop, while loop, for loop. Simple loop is just this, so that loop and loop we can exit the loop with the exit statement. There is an exit statement, conditional exit or unconditional exit of the loop. There is also a next statement if we talk about the loop, so then we can jump to the end of the loop. So next and exit are auxiliary statements used inside the loop. This loop is not synthesizable, it's just for simulation. We've got while loop as well. It reminds of the while loop in any language. So we've got while, condition, loop, just different structure. Again, exit, conditional, unconditional is possible. Next is possible as well. To the next loop, again, non-synthesizable. The only synthesizable loop is a for loop. Why is it synthesizable? With a structure that we have a for, then we have a variable, local variable, then we've got in range, and then that's the trick, because it's synthesizable, because the synthesizer knows how many iterations of this loop is going to happen, and because it knows this, then it can open the loop, it can unwind the loop, and then synthesize it. So this is the only loop synthesizable. And mark the difference comparing to C language. In C language, majority of applications is happening in the loop. So majority of time, the application in microcontroller is spending in some kind of a loop. In VHDL, the loops are used only for multiplying the code, for nothing else. It's done, Dan. Thank you for this semester. Thank you for all the lectures we had together, because in fact, this is our fourth semester meeting. So next semester, we are not having a lecture together. It was a surprise. And thank you very much for, unfortunately, these tough times, because unfortunately, I hate this remote learning, but we were forced, especially this semester. This was a stupidity in my opinion. We survived, bruised, I think, but again, let's hope for better future. So thank you very much, and we'll see each other next Wednesday at 1, if I'm not mistaken. I will give you the room in a separate email in a moment. Any questions, maybe? Any wishes? Nothing. Thank you very much. Have a nice day. Bye-bye. See you next Wednesday.
Thank you. Goodbye.